Hi, chemistry students. This is Mrs. Mitzik, and I am going to teach you about valence electrons, which is the latter part of section 5.2. Let's get started, though, with a review. So I'd like you to write down the electron configuration for polonium. Pause the video and either write the longhand way or you can do the shortcut. It's up to you. So pause and go for it. I'm hoping that you were thinking about your periodic table in terms of the placement of the energy levels and also the orbital types. You know that it's SPDF, you need to memorize that, and you need to know the energy levels. Okay, you've got to memorize that. We will give you a periodic table on the test, but we're not going to give you that information, so make sure you memorize it. We're looking at polonium. It's right here. Polonium, then, if you're making your electron configuration, you will start at the first energy level in the s orbital. You always will because of Aufbau. And then you're going to just go 1s2. This is 2s2. And the superscript is how many boxes I'm counting or how many electrons I'm going along. This is 2p6, 3s2, 3p, 1, 2, 3, 4, 5, 6, 4s2, be careful, this is one less, 3d, not 4, but 3d, and there's 10 across. Be careful, this goes back to 4p6, and then I think you get the drill. You will always add up your superscripts. They should end up being the same as the atomic number of 84. If you happen to be off by a factor of 14, it's usually because you've forgotten the F. Remember, right here, the atomic numbers kind of jump from 56 to 71. This is what's inserting there, okay? And then the other one is inserting there. So don't forget those. Okay, let's move on. In terms of the core, I selected xenon as my core because it's the closest noble gas, closest to polonium in terms of atomic number without going over. And then once I have that, I go to atomic number 55, which is 6s2, 4f14, because I have to go down here, then back up here to 5d10, and then 6p4, because you're 4 across. So that's the shortcut. Much easier. Valence electrons are electrons in the highest occupied energy level of an atom. We like to think of them as electrons that are found in the outermost energy levels located in the s and the p sublevels. So let's have a look at two elements. I've written down the electron configuration for mercury and for sulfur. The outermost energy level is going to be the one that's farthest away from the nucleus. Well, the first energy level is right next to the nucleus. So the bigger the number is, the more outer it is from the nucleus. That was a little redundant, but hey, you got the job done, I hope. So as I'm looking through all these numbers right here, those are the energy levels, and you can see that 6 is the outermost. Since 6 is the outermost and there's no other 6s here in terms of energy levels, first, second, third, fourth, we know then we have 2 valence electrons because there's only 2 in that sublevel. So let's look at sulfur and see if we got it. Here's your first, second, third energy level. Third is the highest or the outermost energy level. We have in those sublevels 2 plus 4, we have a total of 6 valence electrons for sulfur. I'm sure you're thinking, big whoop, who cares about the valence electrons? We're going to find out that there's a specific number that makes atoms content in terms of their valence electrons, and they'll lose and gain electrons in order to get stable. So I just made this fancier. I highlighted my outermost sublevels, and then I added up my numbers for this one in order to get my valence electrons. So I'd like you to figure out the valence electrons for chlorine, lithium, molybdenum. You can use the shortcut if you'd like. Go ahead, pause the video, and then restart. So you can see that I have written down my electron configurations, and this would be my outermost energy level. 2 plus 5, I have 7 valence electrons for chlorine. I kind of jumped ahead here. This is my outermost energy level. I wrote down 3. Is that correct? No, it is not correct. It should be 1. I have 3 total electrons, but my outermost energy level only has 1. So that is incorrect. Keep that in mind. As I'm going along here, I can see that 5 is my outermost energy level, and it has 2 valence electrons. So again, when I'm looking at this is wrong. You can see it's clearly wrong. The second energy level only has 1 valence electron. Here we have 7, and here we have 2. So keep in mind, you're looking at the outermost energy level. Okay, so when I'm looking at chlorine, lithium, and molybdenum, let's look at it in a different way. If I'm looking at this periodic table, I know that everything that I'm always going to write S1 here. It'll be 1s1. The last thing I'll write for this element for the electron configuration will be 2s1. This will be 3s1, 4s1. You get the pattern. You can see that they're all going to be s1, so they're all going to have 1 valence electron. These will all be s2, so they'll all have 2 valence electrons. As we go across here, we're in the p area. We always fill the s before we fill the p, and they're always in that same outermost energy level. So this would be all p1s. This would be 2p1, 3p1. And it would be then 1, 2, 3 valence electrons. Here you would add 4. This would be 5, 6, 7, and 8. And I'm being very careful when I do the 8. Why? I have helium sitting here. Helium only has 2 valence electrons. Why? It only has 2 electrons. In actuality, I keep telling you, helium should be over here because the 1s is the orbital that is filling. Okay, they put it over here because helium has its outermost energy level full, just like all of these other elements. And so because it has a full outermost energy level, it's stable. And these are all called noble gases, and they have a chemical behavior that's very stable because of their electron configuration, or their arrangement of their electrons. So let's look at strontium, niobium, and iodine. You can figure out by using electron configuration how many valence electrons, or if you would like, you can just use the look at where it's located on the periodic table. Up to you how you want to do it. So strontium was located in this column. So you could say it has 2 valence electrons, or you could look at it and say, well, S2 is the last thing that I wrote, so it's 2 valence electrons. When I look at niobium, okay, niobium is actually located over here. Now I put a 1 here. Niobium inserts, this would insert down here. We know that these fill first, so in actuality, niobium has 2 valence electrons. Okay, so keep that in mind. It's not 1, it's 2. The only ones that have 1 valence electron are those found in this column. So I threw that mistake in there on purpose. If I'm looking at iodine, iodine has 7. Why? It's located in this column. It's S2P5. 2 plus 5 gives me 7 valence electrons. So just remember, valence electrons are electrons found in the highest occupied energy level of an atom. Sorry, I was interrupted there a little bit. Let's have a look at level 4. It's a good idea for you to know this. You're going to have to know it at some point anyway, so why not get some extra credit on this unit, hey? Level 4 is talking about atoms and how they want to lose or gain electrons to have 8 valence electrons in the outermost sp sublevels, which will make the atom then stable. It's called the rule of 8. S2p6, it makes them happy, it makes them stable. Okay, the word happy is just to give you a different feeling about it. We prefer the word stable. It makes it stable. So what we're going to do is adjust the electron configuration for an atom to show how stability has been acquired. Let's look at radium. Here's the electron configuration for radium. We know that the outermost energy level is 7, and radium has 2 valence electrons. Radium, however, would prefer to have 8 by losing or gaining electrons. Well, it's got 2, it wants to have 8, so that means it either has to gain 6 or it has to lose 2. It's preferable for uranium then to lose 2 electrons. So when it loses 2, it will get this electron configuration. It will have S2, 6s2, and p6, which puts it in that stable or very happy column. I just have to interject that all of these elements right here, because they're stable, everything's happy for them. They're good, they're stable. They really aren't that reactive because of this. So when you look at the rest of the periodic table, I like to think of them as wannabes. These are the cool guys. They're chill, they're stable. Everything else are wannabes in that they're going to lose or gain in order to obtain an electron configuration that is just like these guys. Also, by losing 2 electrons, what will happen is that radium is going to become a +2 ion. Let's think about that. Typically, an atom has the same number of electrons as protons. If you lose 2 negatives, what happens? You become 2 positive. Makes sense. So let's look at bismuth. Bismuth has this electron configuration. So pause the video and I'd like you to think what are, or point at the valence electrons. You should have pointed here. This is your outermost energy level, and so you have 5 valence electrons. So pause the video and think, well, what would we do so that we could get 8? We're going to gain 3 more electrons. We want to have S2p6. We want to have 8. We have 5, so we're going to gain 3 more to get 8. So that gives us our stable electron configuration. We're now with the rest of the happy guys. So now I've gained 3 electrons. If I gain 3 electrons, what ends up happening to my charge? Well, if I gain 3 negatives, I become -3. So I'm a -3 ion. So putting it all together, what is the electron configuration for magnesium? What is the stability electron configuration? And how many valence electrons are located in the normal electron configuration and the stability electron configuration? Pause the video and go for it. So you can see the ground state, or the normal electron configuration, has 2 valence electrons. So if you look at this one, it has 8. Now, you might have looked at this and thought, oh, it gained 6 electrons, whoa. No, if you notice, the difference between the two is that we've lost the 4s sublevel. Those 2 electrons were lost so that we could get S2p6 in that manner. So by losing 2 electrons, what would be the charge of magnesium? Magnesium would be a +2 charge. That's the end of 5.2. If you have any questions, feel free to ask your teachers. Have a wonderful day.